So I'm going to go through this week's work, or some of, well, 2 hours worth, maybe an hour's worth, because obviously you've got your NEA to do as well. So probably about 10 pages of computer systems. So hopefully some of this I'm going to skip through and just leave it on the screen for a few seconds, because obviously it's been recorded, so you can always go back and pause it if you need to. So we're looking at computer systems themselves, starting with parts of a computer. So I'm hoping that you can all do this without me having to explain it. Right, it's just basic types of computers in your home and the input, process, output, storage model. Right, and then give an explanation for what happens at each stage. Again, it's almost self-explanatory. Input, processing, output, and storage. So I'll leave the words up there in case you want to check your answer, but I'm not going to go over this part. What I will talk about briefly is embedded computer systems. So some people find this a bit confusing, but it's quite simple really. You just have to remember that an embedded computer is a computer inside of something else. So it helps facilitate the function of the thing it's in. So for example, a washing machine could work well enough without a computer. You could have a manual kind of dial, but modern computers have electronic dials, which are built-in computers, embedded computers, and it helps create more function for the washing machine itself. So an embedded system enhances the function of an already existing device. So again, if you think about sat-nav, that if it's built into your car, which is where it would be an embedded system, then that enhances the function of your car, because you can now get to places you wouldn't necessarily be able to do so without a map or something else before. So it's a computer system built into another system. So the computer system is there to aid the function of the other system. So any system that has a computer built into it, that's an embedded computer, an embedded system. Right, so these are the parts of a computer. So hopefully by now these are all familiar to you and you're able to label these correctly. If there's anything on there that you're not sure about, we've got our secondary storage on the right there. So the three main kinds, which are an optical drive, so that's a laser drive, hard disk drive, which is magnetic, and then we have our solid state drive, which is flash memory. So three different types of secondary storage. And then we've got our motherboard, graphics card, power supply, CPU, etc. So hopefully you were able to recognize those parts and label them correctly. Again, this is fairly basic stuff. Right, so let's now look at memory. All right, specifically the difference between RAM and ROM. Right, so RAM and ROM are similar in some ways in that they're both kind of a chip-based memory. However, RAM is random access and ROM is read-only memory. So RAM memory is volatile, so when the power goes, so does everything it stores. Whereas ROM is not non-volatile, so it stays, the memory remains in there even when the computer's switched off, which is really important for the ROM because of its purpose. So the purpose of the RAM is to store the instructions for the current program that's running while the computer's switched on, right? So the instructions and data are stored in RAM for the programs that are currently in use. And as I said, as far as the volatility goes, it's gone when the power's gone. Capacity wise, they're quite big. So sticks of RAM, you saw a RAM stick above, have a capacity around between 4 to 16 gigabytes. They can be small, you can get 1 and 2 gigabyte sticks of RAM, but they're generally, typically now between 4 to 16 gigabytes. Changeable, yes, they are. The contents are regularly changed, right, and can be upgraded to improve the computer performance. So you can swap around your RAM sticks, get more RAM, having more memory on a computer always massively improves the performance. So if your computer's slowing down, the cheapest, easiest way to improve its performance is to upgrade the RAM. Now, in terms of ROM, so what does it contain? It contains a start of information for the computer. So it's called the BIOS, which means Basic Input Output System. So when you press the on button for your PC, the first thing it does is go and read what's written in the ROM, right? And the ROM will tell it what it needs to do next, because there is code hard-coded onto the ROM, which says, right, you first need to, and it will say things like check all of the hardware is functioning correctly, do a little test, then go to your hard disk and load up the operating system, right? So all this information is contained in the BIOS. Now, even though the BIOS is read-only, it's slightly misleading because you can tweak what's in the BIOS. So you can make changes to it, but you can't wipe it. You can't remove stuff from there. You can only change stuff slightly. But generally, it's called read-only memory. Initially, BIOSes, you couldn't change anything. What was in there was fixed. And so when we talk about ROM, we're talking about a fixed piece of memory that can't be or shouldn't be wiped. It can't be wiped. It is always there. It's non-volatile. Right, so non-volatile, always there. Capacity, very small. It only needs enough memory to contain the basic instructions to get the computer running. And changeable, so contents are never changed. So if we weren't doing A level, we would talk about that and say, well, actually, but in GCSE, we'll stick to the fact that read-only memory, the contents are never changed, and the size can't be upgraded, right? So your ROM is normally on your motherboard anyway. So to upgrade your ROM, you need to upgrade your motherboard. So you don't upgrade your ROM. So that's RAM and ROM, the difference between the two, and that could be a potential question. Right, so exam question, example. Here's an example. So most modern washing machines are embedded systems. Embedded systems only have less main memory than non-embedded systems. Describe the two other likely differences between the main memory for a washing machine and the main memory for a non-embedded system. So an embedded system is likely to have more ROM than RAM. Okay, so an embedded system, like your motherboard, will want a piece of code that is fixed, that doesn't change, and that also retains its memory when the washing machine is switched off, right? So embedded systems will have more ROM than RAM. They might have a little bit of RAM, but they will have more ROM than RAM, if any RAM at all, right? So embedded systems don't need secondary storage because everything is generally stored in ROM, right? So it's likely that the main memory and the processor are going to be the same, joined together, and they will have ROM rather than RAM. Okay, so these are aspects of embedded systems, because embedded systems, unlike your PC at home, they're built in. So once they're built in, they're fixed. They're not going to change, and so they're built to so that they don't have to change. They have ROM rather than RAM, etc. Don't have hard drives in there, because they need to be fast, right? So when you switch your washing machine on, you press the button for the main front program, you don't expect to wait 30 seconds for it to boot up, right? And you don't, because it's in ROM, so it's immediately, the memory is available. So that's why in embedded systems, they're mainly ROM devices with maybe a little bit of RAM. Right, so now we're looking at virtual RAM, secondary storage. So very quickly, virtual RAM is when you run out of RAM. So your computer, which uses RAM as its primary source for data instructions, if you run out of RAM, then what the computer has to do is swap information between the hard disk and the RAM. And this will slow your computer down, hence why increasing your RAM will increase the speed of your computer. Right, secondary storage. Secondary storage is what we talked about before. That's non-volatile. So secondary storage is storage that works even when the computer is switched off. Magnetic disks are secondary storage. Optical drives are secondary storage. The advantage of a magnetic disk is has a very high capacity. So we're talking terabytes now for some hard disks, and very low cost per gigabyte, and decent speed access, and also durable, so it'll last quite a long time. However, they're not portable. They have moving parts, so this disk spins. There's an arm that moves across the disk to read the data. So they'd be damaged if you dropped a computer while it was reading or writing. You would damage the hard drive. So and they can also be damaged by magnetic fields because they are magnetic. So if you've got a strong magnet, like you would have in a big speaker, and put it near your hard disks, you could demagnetize parts of it, which means you'd lose all your data. Optical drives, cheap, portable, good for long-term storage. Don't worry about magnetic fields because they're written with lasers, so that makes them immune to that. They're cheap in terms of the fact that the disk doesn't cost much for an average size disk, which is about 4.5 gigabytes. And obviously they're portable as well, but they still have moving parts, so you wouldn't want to drop them while it was reading or writing. The big disadvantage with optical drives is they're very, very slow, easily scratched, and they have a limited capacity. Right, solid state drives. So these are what we're called erasable ROM chips, right? So your ROM is a form of solid state drive, and a solid state drive, remember, like ROM, keeps its memory when the power's off. So these are very portable. All USB sticks are solid state drives, or flash, they're sometimes called. So, but as they are just static, there's no moving parts, you can drop them, bash them about, and it doesn't affect them whatsoever. But they are more expensive, and in terms of durability, they do have a limited number of read-writes. What that means is you can only read and write to them so many times. However, in recent years, the number of read-writes means that they should last you 10+ years still. And most people don't keep their hard disks that long. But they do have a limited lifespan in terms of the times you can read and write from them. Right, another form of storage is cloud storage. So you just imagine cloud storage literally as a hard disk in a different location from where you are that you connect to via the internet. So it's someone else's hard disk, you connect to it via the internet, via some service. So if you were doing cloud storage with Microsoft, you would use OneDrive. If you were doing cloud storage with Apple, you'd use the iCloud. So each cloud storage device usually has a name that you know to connect to it, but it is literally just a hard disk somewhere storing your information. But the advantage of that is that you can access it from anywhere. If you're not at your computer, you can access it from someone else's computer, or anywhere in the world, and everything's backed up for you automatically, so you'll never lose your information. And here we've got the advantages and disadvantages here. They tend to be cheap as well compared with buying a 1 gigabyte hard disk. In the short term, they're cheaper. Over the long term, that's not necessarily true. If you might pay £5 a month for your storage, but over a year that could, and you can end up being able to buy a hard disk, but then again you have the fact that someone else is storing it for you. You don't have to worry about backing up or it going wrong. So there are lots of advantages for cloud storage, but the obvious disadvantages are that you have to have a network connection to access the information, do rely on someone else. So if something went wrong with their computers, then you could lose your data. Need to remember a username and password. Yes, that's normally the case when you log into a cloud service. Large companies are more likely to be hacked than you are. So the data could be at risk, but I mean, it depends what kind of data. If it's just photos, I mean, you're probably not that worried. Someone else seeing a copy of you eating your birthday cake. And again, if you looked at it per unit of time, the cost can mount up over time and end up being more expensive. Right, so here's 5 examples of cloud storage services. Right, now the von Neumann systems architecture, went over this a few weeks back, so just a quick refresher. So if you remember, the von Neumann architecture is the type of architecture you get on a CPU. So it means that when the CPU reads data, the data that is stored and the instructions are both stored in the same place. So for the von Neumann architecture, both the data and the instructions are stored in the same memory space. So this means that when you're doing the fetch, decode, execute cycle, you can only fetch an instruction, then a piece of data. So you have to fetch them one after the other. You can't get them both at the same time because they're both in the same memory, and you have to read the instructions from the memory one at a time. So this process is easy to create, which made computers cheaper. However, there are other architectures that don't have that limitation and are quicker because of it. But the architecture, the von Neumann architecture, just means that you store both your data and instructions in the same piece of memory. Right, so the CPU, again, you can read this for yourself. Which part of the CPU controls the fetch execute cycle? The control unit. So it's the control unit that controls fetch execute cycle. And then there are 3 other parts of the CPU that are important. So we've got the clock. So the clock is literally that. It ticks a certain amount of times per second. And this tick synchronizes when the instructions are read and sent. So everything needs synchronizing. So every time that clock ticks, an instruction is read, so on and so forth. And the number of times per second is the clock speed. So we're talking gigahertz for most modern computers, which is billions of times per second. So the clock is responsible for that tick, so that increasing the program counter, fetching the instructions. The buses, these are connections that pass data and instructions around. Okay, so you've got different types of buses. You've got the address bus, the control bus, and the data bus, and these are collectively known as the system bus. So a bus is what the data and the instructions travel along from going from the RAM to the CPU, or from the graphics card to the CPU. So they travel on things called buses. There are 3 types of buses, which 3 different types of things travel along. So you've got your control, you've got your addresses, and you've got your data. Each of these 3 pieces of information travel on separate buses, but together they're known as the system bus. Right, and then you also have registers, which are very fast memory, which faster than RAM, and these are used to store the fetch, decode, execute instructions because they need to be done billions of times a second. So the registers are where these instructions are stored on the CPU. So what is the name of the connections that move the instructions from the main memory to the registers? They're called buses. Right, so cache memory. So let's have a look at cache memory. So this is a diagram of memory on a computer with the largest and slowest at the bottom, smallest and fastest at the top. So on our CPU, so here's our processor. Now today, processors can have multi-cores, right? Multi-cores. So it's like mini processors on a big processor. Okay, so each core can do its own processing, and each core will have its own cache. So cache is fast memory that is the first place that the CPU goes to access its data. So this core here will, when it's looking for data instructions, will go to the level 1 cache to see if its instruction is in there. If it isn't, it will then go and look in the level 2 cache. And this level 2 cache is shared by all of the cores. Right, so any instruction that it uses all of the time will be stored in the level 1 cache because that will make it lightning quick. Right, instructions that are only occasionally or less, use a little bit less than the ones that are used all the time will be stored in the level 2 cache, and then the next level of cache is on the motherboard, and finally, if the information is not in any of those three, it goes to the RAM. Okay, so the bigger the cache, level 1 cache, the faster your processor. The bigger the level 2 cache, the faster your processor. The same with level 3 cache. So these cache sizes affect the speed of a CPU, and then finally it's the RAM size of your RAM that also has an effect. So memory, registers, got registers, cache, RAM, and then secondary storage. So what was the question for this? So explaining here, cache stores the instructions, data that computer uses regularly and thinks it's likely to use for the current program. It's faster than RAM, blah, 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 blah. Level cache is close to CPU. I've just explained all of this. Okay. Right, so explain three factors. No, explain how these factors, there are a number of factors that affect the speed of the processor. Explain how these factors affect the speed of the computer's CPU. Right, so clock speed, the faster the clock speed, the more instructions per second that the CPU can perform. So the faster it's going to be. Number of cores, right? So for GCSE, more cores means the computer can process more tasks at the same time. More cores equals faster computer. Now this is not always the case, but we're at GCSE, so we will stick to this. More cores, faster computer. Cache size, so the cache stores the most frequent instructions. More cache means more instructions can be stored, which means faster computer, right? So just straightforward, basic answers there. More cache, more instructions, faster computer. Right. I'm going to finish on Boolean logic, so I'm going to do this and I'm going to stop. Right, so truth tables, Boolean logic, and logic gates. So if we remember back, we have different logic gates. We have a logic gate called a NOT gate, and this has an input A and an output Q. And in our truth table, we can only have two possible inputs with one input inside there. So 0 and 1, we're in a binary system. So 0 and 1 and 0 becomes 1 and 1 becomes 0 because NOT inverts everything. So it has the opposite of the input. For an AND gate, well, we need two inputs for an AND gate. You can't AND something together, there's only one input. So we have two possible inputs and then four possible combinations with two possible inputs. So if both inputs are 1, then the output is also 1. Both inputs are true, the output's true. Both inputs are on, the output's on. However you want to talk about the Boolean version of 0 and 1. Right, if both inputs are not 1, then the output is 0. Now for an OR gate, it's the opposite. Only if both inputs are 0 is the output 0. So if either A or B are 1, then the output is 1. And then complete the table to show every possible combination of the logic inputs A, B, and C. So if we've got 3 inputs, that means we've got 3 bits, and 3 bits, as we know, if we count in binary, 3 bits is 7, 0 to 7, which is 8, right? And here we count from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. So these are all the possible inputs if we had 3 logic inputs, or all the possible combinations of those 3 inputs, right? And I don't recall ever seeing a truth table that had more than 3 inputs. Right, so we also have logic circuits. So this is a logic circuit, and this is a basic truth table for the logic circuit. So we've got A or B coming in there, and then not P. So A is 0, B is 0, P therefore is 0 because neither A or B are 1, and then the output is 1 because we invert it. All of the others are 1 because they have a 1 coming in, and then we invert it so the output's 0. Don't worry about the final solution. This is how it's presented in an exam. You don't have to do that. Right, so what's the logic statement for this circuit? So so Q equals Q equals not A or B, right? So we always work backwards. Q equals not A or B, right? Not A or B. And then we have another logic circuit here. It says draw the logic circuit for Q equals C or A and B. So when we're drawing this, say, right, so C has to go into an OR gate. And that's C and A or B. Or is that the one below? Okay, yeah, it is. Right, okay. I was going to say because that's wrong. Right, C and A or B. So C and A or B is here. Draw the logic circuit for C or A and B. So C would have to go into an OR gate, and A and B would have to be there to connect with C. So when we're drawing logic circuits, we just follow it through. So we know C is part of an OR, and so is A or B. So A and B goes into an OR, but the A and B goes into the OR. So again, we can kind of work backwards to build our logic circuits. So that's the C or A and B. A and B or C. So we'd have a, if this was the diagram, we'd have A going into an and we'd have a B or C diagram there. A going into an and, B or C going into there. Right, that has been half an hour of your time. I'm not going to go on any longer. I'll stop recording there.